Welcome back to our series on multivariable calculus. In this episode, we're going to look at derivatives. That is, derivatives of these three-dimensional functions we've been looking at. Space curves, otherwise known as vector functions. Fortunately, the derivative of a vector function isn't much different than the derivatives of the functions that you're used to in a flat plane. If I want to calculate r prime of t, of course the definition of the derivative says this is the limit as delta t approaches 0 of the ratio of r of t plus delta t minus r of t, all divided by delta t. In terms of a picture, what this means is as the curve flows through space, recall that r of t is a vector from the origin that points to a location on the curve. R of t plus delta t would just point to a later point on that curve. And of course, the derivative would represent the vector that joins them. This would be delta r. By allowing delta t to get smaller and smaller and smaller, it moves these two vectors closer and closer and closer together until ultimately delta r's magnitude will shrink to 0. Of course, the 0 magnitude vector isn't really very useful to us. It wouldn't have a direction and it wouldn't have a magnitude. But by dividing by delta t, we get to preserve the magnitude and direction of delta r because the derivative has a magnitude even though delta r would shrink to a vanishingly small magnitude and a 0 direction because its magnitude would go to 0. The ratio of delta r to delta t preserves that. In essence, because r is defined in terms of three independent functions that are all defined by t, I can simply apply the same rule to the derivative to each component of the vector. That is, the derivative of the vector will be r prime of t. And remember, that's a vector. And that will equal the vector f prime of t, g prime of t, and h prime of t. The question really is, how then do we geometrically interpret this derivative? What does the derivative of a vector function really tell us? Well, in the same way that for a two-dimensional function in a flat plane, the derivative provided the slope of the function, we're going to get something very similar from these space curves. It won't necessarily represent the real slope. After all, for a 3D function, that slope could point in any direction at all. Up, down, left, right, it could come towards us and away from us. So the whole idea of one variable increasing with respect to another is lost in 3D space. But it will give us one really powerful result, and that is the derivative of a space curve forms a new vector that is always tangent to the curve at whatever t value we want to plug in. Let's take a look at that. The function we're going to look at is one we looked at yesterday. R of t is equal to cosine t, sine t, and t. And you'll recognize this as a helix. This one is a helix that basically rotates around the z-axis. So let's draw a quick sketch of it just so we can refamiliarize ourselves with it. At its starting point, when t equals 0, this will be 1, 0, 0. So it will be on the x-axis, 1 away from the origin. And then it will spiral around in this direction, climbing the z-axis and forming a perfect circle centered on the origin in the xy plane. It'll just be a circle that elevates every time it rotates around. Well, if this represents r of t, let's take a look at the derivative of this function and then further look at what that derivative gives us at unique locations on the curve. Because we already have a pretty good idea of how this curve behaves, we can then look at what the derivative represents for it. So r prime of t will be, the derivative of cosine is negative sine of t. The derivative of sine is cosine of t, and the derivative of t is 1. So there's the vector r prime of t. That is the derivative of this particular helix. Now we know that the location of the helix begins at t equals 0 at the point 1, 0, 0 on the x-axis. What is the derivative at that point though? Well, let's plug 0 into r prime of t. That is r prime of 0. At t equals 0, of course, sine of t is still 0, cosine of t is 1, and the z component is always 1 in the derivative. That means the vector representing the derivative at time t equals 0 does not point in any direction along the x. That means it's perpendicular to the x-axis, and yet it points down the positive y-axis and it points upward. So let's draw that in. From this point, that would be a vector that would look like this. This would be r prime of 0. Well, that looks very much like it's tangent to the curve at that point. That is, it actually describes the direction the curve is going as it leaves the x-axis. As it leaves the x-axis, it's going to head straight down the y-axis, and it's going to head slightly upward in order to begin forming this helix. Now, it won't always remain pointing straight down the y-axis. It only does so at its initial point, r equals 0. As t increases, this vector is going to bend. It will continue to move upward a direction 1 all the time, but it will begin to bend in this direction. Let's take a look at the next point. The next point I want to look at is right here on the curve where we've reached our extreme, we're as far down the y-axis as we're going to get. That would be pi over 2 for our t value. So r prime of pi over 2 would be equal to, well, the sine of pi over 2 is 1, so this will be negative 1. The cosine of pi over 2 is 0, and the z component is always 1. So look at what happened to the vector as we turned through 90 degrees. Now, this vector, that is the derivative at pi over 2, points down the x-axis in a negative direction. It doesn't have any change in the y, so it's perpendicular to the y-axis, and it moves upward. So that means it's going to be right here, again, moving away from me, and that will be r prime of pi over 2. This vector will basically remain tangent to the curve and will continue to turn tangent to the outside edge of that circle and constantly climbing. An interpretation of the slope or an interpretation of the first derivative of these vector functions can be drawn from physics. If t actually represents time, then we can consider r of t to actually represent displacement. That is, it's an indication of where the object is and where it's going, basically its trajectory. If that's the case, then the first derivative of displacement would give me velocity. Velocity would be v of t, a new vector, and it's equal to r prime of t. Now, this is not to say that the t values in all of our parametric vector functions are going to represent time, or that all of our RTs are actually going to represent displacement. But it gives you a nice analogy that when you're working with space curves, you can always think of them as representing the position of a particle as time goes on. Therefore, the original vector indicates its displacement, its location over time, and its first derivative indicates its velocity, how fast it's moving and in what direction. How fast it's moving is significant too. In physics, we distinguish the magnitude of the velocity with the velocity by calling the magnitude of the velocity the speed. So let's calculate the speed of this particle as it travels upward on its helical trajectory. what I want is the magnitude of r prime of t. And of course, knowing that r prime of t is negative sine t cosine t1, I could just put that through the Pythagorean theorem. So this will be the square root of sine squared of t plus cosine squared of t plus 1. Sine squared plus cosine is 1, so it's 1 plus 1, or the square root of 2. So the magnitude of this velocity vector, that is its speed, all the way through this trajectory is a constant, radical 2. Its direction is constantly changing, but its magnitude remains the same. That is not always the case. The magnitude of the velocity vector for some trajectories will definitely increase or decrease. Let's take a look at a different function where that's the case. This function will be a little bit easier. We'll look at r of t equals t cubed plus 2, 2t squared, and 3. Once again, if we think of this as a trajectory, this would be the location of the particle as a function of t. It would give its displacement. R prime of t, that is the velocity, would be equal to 3t squared, 4t, and 0. Now notice, at t equals 0, the velocity will be 0. But it's not going to be 0 immediately before that or immediately after that. If I plug any non-zero value in for t, I'm going to get a value for its velocity, which means the speed wasn't 0 before t equals 0, and it wasn't 0 after t equals 0. If this were a regular slope in 2 dimensions, then we would say that the slope were horizontal at this point, that it had 0 velocity at this point. Well, one of those two statements is also true about these vector functions. The velocity certainly is 0 at t equals 0, but it's unfair to say that the slope would be horizontal, because after all, this is a 3-dimensional vector. It could really be pointing in any direction. It just so happens that at that instant, its magnitude goes to 0, and that's the reason why its value is 0, 0, 0. It's not because it's horizontal and has a magnitude, it's that its magnitude is actually 0. So the velocity goes to 0 at this point. It has no direction at this point. How can we physically interpret that? Well, here's a graph of this exact function, and I think you can see why it has a velocity of 0 at t equals 0. What this function shows is what's called a cusp point. A cusp point is when the trajectory rapidly changes direction. When that's the case, the velocity will be 0 at that point, but you'll also notice there's nothing about that unique point that we would deem horizontal. If we graphed it, we wouldn't see that it was horizontal at that point. Okay, the final concept that we're going to talk about is the idea of the magnitude of this first derivative. We know that it represents the velocity and the magnitude is the speed, and that's often important to us. But sometimes I'm taking the derivative because all I'm interested in is the direction of the curve at that point. I really don't care about its magnitude. So I don't necessarily need the full velocity vector. I just need a vector that points in the direction of the velocity vector. As a matter of fact, it might even be better if the velocity vector had no magnitude at all or had a magnitude of 1. Here's how we go about doing that. We talked earlier about forming a unit vector, and that's what we're going to do. We're going to form a unit vector for r prime, and we're going to call that t. The reason we use t for this is that this represents the tangential vector, and because it's capital, it represents a tangential unit vector. T, of course, will be equal to r prime of t, the actual vector itself, divided by the magnitude of r prime of t. By dividing any vector by its own magnitude, we can virtually guarantee that the magnitude of the vector formed will be 1. It will be a unit vector. So taking the tangential unit vector from the magnitude and direction of the first derivative allows us to find a vector that is tangential to the curve and has a magnitude of 1. And we'll see this tangential unit vector will have some use for us as time goes on. Well, that's about it in terms of the application of the derivative. The good news is derivatives for vector functions are not much more complex than derivatives were for the functions you're already used to taking derivatives of. If you can take the derivative of f of t and g of t and h of t, then you can take the derivative of r of t. The implication of that is you can think of all these as being trajectories where the location of an object is provided by the radial vector. Therefore, its first derivative can be seen as the velocity vector. Its direction will be tangential to the curve at every point, and its magnitude will tell you the speed. If in fact you want that direction and you're not really very concerned with what the magnitude is, you can always find the unit tangential vector, which would be to take the velocity vector and divide it by its own magnitude. Well, we will see going forward that we'll get lots more applications of the derivative of vector functions.